This is Kevin, and he has been left alone with only $16.67 to spend on the things he really needs. That means he has to allocate certain funds to buying food, beverages, and of course, toys. So, if the food costs $4 and the beverages $3.67, he cannot fit a toy that costs $10. That is just outside his budget. So, what can he do? He can avoid buying the toy from a large retail store and instead opt for buying it cheaper at a yard sale or at his local neighborhood toy store that sells similar things for a lesser price, where he found it for only $8. So now he has fulfilled all of his needs within his daily budget and can eat, drink, and play with his new toy. But then he starts to think about the toy situation. Why don't similar looking trucks have a similar price tag as well? And it turns out that the expensive one requires more work to fabricate and the use of more expensive materials than the cheaper one. But in the end, they look more or less the same, which means that the cheaper one has a better fabrication strategy with less expensive materials that do the job just as well. The same is true for our real-time rendering. If we want to depict a realistic-looking scene with quality high-res textures, it can take a lot of time to render. So we have to consider if there are any approaches that can give us a similar-looking result for less time, which is why today we're talking about rendering on a budget, efficient texture, and material management. So 16.67 is a budget we are working with as well, but do you know why? If it's not clear enough by now, I'll add the units as well, and we can notice that this is usually the time we have for a 60 frames per second real-time rendering application. We can observe our budget through different departments such as game, draw, and GPU threads, like we've explained in our previous video, and see where we are allocating most of our funds, and if any area is costing us more than we have. In this case, we can see that the GPU thread is taking almost all of our budget. Even though GPU is essential for all shader programs, including pixel processing, we have to find out what is causing this issue and if we can reduce it somehow. And it has to do with the amount of data that needs to be processed, which is taking a lot of time. But we have talked about the inclusion of the GPU that can handle the computation of large data amounts in parallel, like 30 teraflops at least, which is around 30 trillion floating point operations every second. So how are we still having an issue? Usually the reason is the inability to access all the data in time and transfer it to the GPU fast enough, which has to do with a very important issue of different forms of memory. Now, if I give you this number and ask you to remember it, you might find it difficult since there are a lot of numbers, but we can remember it by storing it in our short-term memory and forget it several minutes later. But if I divide them into chunks like this, you may notice that this is a time and date format for lunchtime at Christmas, for example. By using previous knowledge from our long-term memory, we can remember new information more efficiently and remember it for longer. But in this case, we are talking about different forms of memory for a computer. We can definitely notice the hard disk drive or the HDD, which is a data storage device that uses spinning magnetic disks to read and write information. It is commonly used for long-term storage due to its high capacity and relatively low cost. We can also recognize the USB flash drive, which is a portable data storage device that uses flash memory to store and transfer files. It has no moving parts. It is compact, durable, and connects to devices via a USB interface. From these, we got the solid-state drives or the SSDs. These two types of memory are non-volatile, which means they do not require power to store the data, which is why we use them for long-term data storage, which is similar to our long-term memory. We might be aware of additional memory devices such as RAM or the random access memory, which is a form of a volatile memory unit, meaning it requires continuous power supply to retain data, and we use it for more immediate tasks that are required for CPU processing, similar to our short-term memory. But did you know that what we call RAM is not that precise? Actually, this is called a dual inline memory module, or DIMM, which has several DRAM chips, where D stands for dynamic, meaning it requires refreshing thousands of times per second in order to retain data. We also have the VRAM, which is the video random access memory, located close to the GPU cores and is used in graphic card computations. But perhaps even fewer people know that we have another version of RAM, which is called SRAM, where S stands for static, and it does not require constant refreshing because it works with flip-flops. It is located close to the CPU, storing frequently used data and instructions. This form of RAM is also called cache memory, and it is made out of L1, L2, and L3 parts. Finally, there are also registers within the CPU which serve as immediate storage for the CPU operations, such as arithmetic and logic ones. So now that we know about all these different memory units inside our computer, we can talk about the memory hierarchy, which organizes memory components based on their access and response times, ensuring that frequently accessed information is obtained faster than less frequently used data. But is the access time the only thing that is important, or are there any other aspects that should be taken into consideration? When it comes to memory hierarchy in real-time rendering, alongside the access time or latency, we need to take into consideration the capacity and the bandwidth or throughput. So capacity refers to the total amount of data measured in bytes a memory or a storage unit can hold at any given time. To explain it simply, let's say different bucket and barrel sizes can accommodate different amounts of water. Access time refers to how quickly a specific piece of data can be retrieved from memory or storage. It is essentially the latency in memory systems, and it is measured as the time elapsed between a request for data and its delivery to the processor or requesting component. To explain it simply, let's say that the closer you are to the faucet, the faster you will have access to the water to fill your bucket or container. And finally, we have the bandwidth, which refers to the amount of data that can flow through a system or be transferred between components like memory units and the processor in a given amount of time. It is measured in units like bytes per second. To explain it simply with water again, it is like having different diameter pipes that can output different amount of water based on their size. So now we are aware of all the important aspects of each memory unit, the capacity, latency, and the throughput, as well as which memory units are mostly located within our computers, like different forms of RAM and SSD. But how can we connect them together? Firstly, let's take a look at the capacity of each memory unit. Starting at the very CPU, we can see that the registers attribute up to 2 kilobytes, followed by SRAM or cache memories L1, 2, and 3, which contribute to 64 kilobytes, 1.25 megabytes, and 25 megabytes of shared storage throughout all the cores respectively. After which we have the DRAM or VRAM, which has a significant upgrade of an average of 16 gigabytes, with the SSD having around 1 terabyte usually, and HDD having 4 terabytes on average. It is important to note that cache memory capacities are calculated per core, which means that more storage is available in the SRAM cache memory. However, it seems very little when compared to DRAM and SSD, so why don't we use those instead? This is where we take access time or latency into consideration. As we can see, the registers in the CPU are the fastest, theoretically capable of writing and reading data at a fraction of a nanosecond. Around 2 times slower is each of the L1 and L2 cache memories, at around 1 nanosecond, before arriving at the L3 cache, which is 5 times slower than the previous one. We can notice that DRAM is 2 times slower than L3 at around 15 nanoseconds, but still significantly faster than the SSD, which is where we see a drastic deterioration of access time. 5 times slower than DRAM, at around 50 microseconds to access data, not even mentioning the HDD, which has a latency of 10 milliseconds. We can see the latency data spreadsheet here and notice a connection. The closer we are to the CPU, the faster our access time is, but we have less capacity. This means that we should be using DRAM and VRAM as much as we can when it comes to real-time rendering, since they are the middle ground between low access time and high capacity. We cannot rely on SSD as a viable source of quickly accessible data due to the large latency. But can these DRAM units transfer the data in a timely manner to the CPU and GPU? This means we have to consider the bandwidth. As could be expected, the cache memory has a pretty high bandwidth of around 500 gigabytes per second, with DRAM and L3 cache having 10 times less. But what's very interesting is that the graphic cards are equipped with VRAM that has the bandwidth similar to the cache memory and allows for a pretty fast transfer of data, as opposed to SSD, which has a more than 100 times less throughput. This means that if we are able to transfer all of our relevant data to the VRAM, we should be able to run our real-time rendering applications without any issues, since all the data is available for the GPU to compute, with adequate access time and capacity. This means that if we are able to transfer all of our relevant data to the VRAM, we should be able to run our real-time rendering applications without any issues, since all the data is available for the GPU to compute, with adequate access time and capacity. Now that we are familiar with the memory hierarchy, we can focus on one of the most memory-based aspects of real-time rendering that uses VRAM, which are the textures. As is said in the book Real-Time Rendering, a surface's texture is its look and feel, similar to textures in an oil painting. However, in computer graphics, texturing is a process that takes a surface and modifies its appearance at each location using some image, function, or other data source. If we are using images as textures, like photographs, we can generally provide a more realistic depiction of a surface or material because these images capture the natural variations, imperfections, and details that occur in real-time materials. If we use images, it requires a lot of memory. On the other side, we have procedurally generated textures, which are highly flexible and efficient in scaling and resolution, but they can sometimes lack the natural realism of photographic textures. They take a toll on performance and less on memory. Given that the images create a more realistic depiction and are tied to memory, we will focus on image-based texturing, or more specifically, bitmaps. which represent a map of bits or a spatially mapped array of bits that specify the color of each pixel in a rectangular array of pixels. The number of bits devoted to an individual pixel determines the number of colors that can be assigned to that pixel. So if we only have a black and white color for a pixel, we only need 1 bit per each pixel because the pixel can either be black or white. Can we calculate how many bytes we would need in this case? Pause the video now and give it a try if you'd like. In this case, we have an array of 8 by 8 pixels and we need 1 bit per pixel, which would be 64 bits. But we can divide this by 8 in order to get 8 bytes. If we are familiar with this, now we can go to a more complex example. So we have our monochrome image of only 100 by 200 pixels, where we use 1 bit per pixel and take almost 2.4 kilobytes of data. Next to it, we have a grayscale image, which has a whole gradient of gray colors, 256 to be exact. Basically, the intensity of the pixel, where we are using 8 bits for each pixel, which means that we are using 8 times more memory. We just have to mention that we are excluding additional memory consumption since we want to focus on how much the increase in bits per pixel influences the size of the image. If we plan to use 24 bits for each pixel, which is equal to 8 bits for each RGB channel, we will have more than 16 million colors of data, or 58.6 kilobytes, which is more than 20 times larger than the monochrome image. Additionally, if we include the alpha channel, we will have 4 channels, RGB and alpha, with 8 bits each and 32 bits in total per pixel, resulting in 78.1 kilobytes of data. Finally, if we want to capture even more data than the human eye can grasp, like for HDR images, we can have even 24 or 32 bits per each of the RGB channels, resulting in up to 96 bits per pixel and an increase of 4 times more than the regular 24 bits per pixel image. So you can see how different amount of data per pixel can result in an increase of memory by several orders of magnitude. Since 24 to 32 bits per pixel images are mostly used in real-time rendering, we'll focus on those and check out this example that represents the diffuse image of the material. If we use a 2K texture with 32 bits per pixel, when you do the math, this can take up to 16 megabytes of data, which seems small. But this is not even taking into consideration all the additional images we would need for this material, like normal, roughness, ambient occlusion, specular, metalness, and similar, which can build up to around 50 megabytes per material. But we have a lot of gigabytes of storage in the VRAM. Surely we can accommodate mere 50 megabytes per material, no? It would seem that way, but usually VRAM has a dedicated space for texture storage, specifically which can be restricted up to 1 gigabyte, for example. This means that we are restricted to using 20 materials, and even for an interior scene, this can become an issue. This is why we have to talk about compression, specifically texture compression, which is a specialized technique used to reduce the memory footprint of textures in VRAM while maintaining efficient access and acceptable visual quality in the SSD. It involves encoding texture data in a format optimized for GPU decoding, allowing textures to remain compressed in VRAM and be sampled in real time during rendering. So if we go back to our example here, we would expect that this texture would use up 16 megabytes of storage space. However, we can apply a block compression or BC to reduce the size of this texture during real-time rendering. So how is this done? Block compression or BC reduces texture size by dividing it into 4x4 pixel blocks and finding the 2 most distinct colors with each block. These 2 colors are stored and the other colors are interpolated using indices. This approach significantly reduces memory usage, typically achieving a compression ratio of about 6:1, reducing, for example, a 16 megabyte texture to about 2 or 3 megabytes, depending on the format. This produces similar looking results while reducing the memory size on the VRAM, which helps us stay within the budget. So it seems we have handled the issue of large textures and the restriction on texture slots in VRAM for scenes such as this. But what happens if we have an open real-world exploration with a myriad of textures and extremely high resolution, like 32K pixels? Will texture compression be enough to help us stay within the 16.67 millisecond budget per each frame? Or can it create problems? Let's check it out. Let's say we are moving toward a house in a village or a town setting. The structures that are far from us are displayed using the same size textures as those that are close to us, and this can take a lot of unnecessary memory from the VRAM texture pool, a portion on VRAM specifically dedicated to storing textures. We can see this issue in Unreal if we get the message about exceeding the streaming pool budget, which means that even though we have compressed textures, they are still taking a lot of memory on the VRAM. Now we can go to our textures and, for example, reduce the normal maps to 1024 and displacement and bump maps to 256. as we will not lose that much detail, but we have to be careful here as well. We have to take into consideration the compression format, as the wrong compression format can cause artifacts and also determine by how much to reduce the texture size. We can also consider using the uncompressed version for small textures of 256 pixels, as is the case here for a height map. However, for large-scale world textures, we can run into an issue of exceeding the streaming pool budget, even with the implementation of these reductions. And if we have enough room in our VRAM, we can extend the budget from 1 gigabyte to 10 gigabytes and create a realistic real-time depiction of our texture, as can be seen here. But we have to take into consideration the optimization aspect here and the fact that increasing the streaming pool budget decreases it for other shaders within the rendering pipeline. But there are also other issues that can occur. The first is this. When we have large textures, we also have a lot of texture elements or texels that are covered by a single pixel. This means that for each pixel on the screen, we have to average out a significant number of texels, 8 in this example here, in order to compute the color of our pixel. This can be done in the following ways. One approach is to use the nearest texel color and assign that for the pixel color, while the other approach, called bilinear interpolation, requires even more calculation, where we average the color of two closest texels in one direction and also in the other direction to get the final pixel color. You can see the difference between these approaches when compared to the original image in this example. But whatever the case may be, this form of computation slows down the performance of our application. But that is not the biggest issue. This flickering is, as we are constantly calculating the color of the pixels, which can vary based on our movement, so it would be better if we did some pre-filtering maybe. Here is where we can introduce the concept of Mipmaps or MIPS, which are pre-computed downscaled versions of a texture that are stored alongside the original high-resolution texture. They are used in real-time rendering to improve performance and visual quality by selecting the most appropriate level of detail based on the distance and size of the texture on the screen. We can also refer to Mipmaps as a resolution pyramid, where the base is our original image, in this case a 128 by 128 image, which represents level 0. And as we are moving to the top of the pyramid, we are decreasing the amount of pixels in reference to the original image by half. So going to 64 pixels, 32, 16, 8, 4, 2, and finally 1, which makes 7 levels of Mipmaps. The MIP in Mipmaps comes from the Latin phrase multum in parvo, which means much in little, referring to the existence of a lot of different resolution maps inside one texture. So basically, we are doing downsampling or pre-calculating the average color of 4 pixels in one MIP level to generate a new color of a pixel in the MIP level higher than that. That means that the flickering we had from before is now resolved, as we are just sampling and not calculating the pixel color. But do Mipmaps help us in decreasing the VRAM texture pool budget? Not quite, since all these extra maps contribute to the additional size, even though they're of lower resolution. However, if we put them all together, the memory is only increased by 1/3, which we can validate by taking 1/3 of the initial image and overlapping the higher levels of Mipmaps and filling in the blanks with the parts that go outside it. So Mipmaps seem to increase the texture pool size by 1/3, but they drastically improve performance, as we are usually using 1 texel per 1 pixel. Let's take a look at this example from before, where we have a high resolution texture where 8 texels are covered by 1 pixel. And by changing this, we are reducing the necessary computation during rendering. The Mipmaps basically allow us to have 1 texel per 1 pixel in camera's view, which cuts down on the computation for calculating the average value of a pixel based on multiple texels. That means that the things that are closer to us have a higher texture resolution that is loaded in the memory, while the things that are further away have a lower texture than that. As we are moving towards the low resolution textures, we are getting a higher version of the Mipmaps, keeping our depiction as realistic and crisp as possible. But how is this calculated? Basically, we take the amount of texels that are covered by 1 frame buffer pixel, and we use them as ratio R. The binary logarithm of this ratio gives us a number that represents the Mipmap level. If we get a real number that is larger than the one as a ratio, we can either take the nearest Mipmap level corresponding to it, or we can take the linear interpolation between the closest 2 Mipmaps and also perform a bilinear interpolation of the texels to calculate the number for the pixel. Now, it seems that we have handled all the issues that can occur within our scene and optimized the memory by using compression and the performance by using Mipmaps for both interior and exterior scenes. But let's go to this example and consider an issue that can occur. We are looking at a large ground asset that has a high resolution texture in order to keep the details crisp. What MIP level do we load for the texture? Since the texture is close to us, we have to use a lower MIP level or the high resolution image, but a lot of the texture is not visible in the scene, and yet we have to load the entire high resolution image or Mipmap into memory. The same thing can happen if we are observing some of the textures up close, but they are occluded by other assets in the scene. We still have to load the appropriate MIP level maps in its entirety. So here is where we can introduce the concept of virtual textures. In order to understand the concept of virtual textures, we have to go back to the memory aspect we covered before and introduce the topic of virtual memory. Virtual memory is a memory management technique that creates an abstraction layer between a computer's physical memory, like RAM, and storage, like SSD, allowing the system to use a portion of the storage as if it were additional RAM. This enables programs to operate as though more memory is available than what is physically installed on the system. But what does this look like in practice? Let's check it out on this example. Imagine that this is your desk where you work as a news reporter. The free area of the table is your limited but available DRAM or VRAM, things that are needed immediately and that we can access and transfer quickly. And then we get two pieces of information that we can research for an upcoming news report. And this takes a portion of our free area on the desk. But there is still a lot more left, and we can continue researching and reading without any issues. Gradually, we keep getting other pieces of information that fill up the entirety of our desk until there is no free space for anything new to arrive. But as it usually happens, we get other pieces of information as well, and we are faced with a problem of not being able to place this additional piece of information on the table. However, given that we can only read one document at a time, we come to an idea. We can take one of the documents we are not currently reading and place it in our drawer. It is not immediately accessible, but it is close by. Think of the drawers as our SSD. It has a slow bandwidth and access time, but it has a lot of storage that we need now. However, in order to know where we placed it, we create a small node that we leave on the desk so we can find it faster later. And then we have enough space to place the new piece of information on the desk. And we also have a way to deal with the lack of storage on our desk when new pieces of information come, and a way to keep track of where everything is. But what if we need all the information we have to be displayed in front of us, but we only need certain portions of those documents, like only need a certain paragraph or a certain sentence? Retrieving and swapping things on the desk can be time-consuming and produce low performance on our end. So what do? We can always cut out all the documents into smaller parts, like paragraphs, titles, and similar chunks, and then keep the ones that we really need while storing the rest aside to be used at a later time, with even more sticky notes to help us navigate, but more space for the things that we really need. We can do the same thing for textures. We can cut them down to tiles of 128 by 128 pixels in each mipmap, and then just stream the ones that are needed based on our view and our needs in the scene. So we can take our examples regarding virtual memory and apply it to virtual textures, which is shown here, coloring parts of the documents in different colors to indicate different parts of our textures. But that can cause a lot of sticky notes on the table as well. So why not put all the little parts together as a collage of different parts of the textures, which is why this approach is sometimes called mega textures, and make one sticky note that tells us how to look up different materials as a whole. In a real-life example, this would be the mega texture, equivalent to the collage of differently colored document parts, having all the necessary chunks of the textures that are visible and at a specific mipmap level. And this would be the indirection texture, equivalent to the sticky note that tells us where each texture comes from if we need to look it up for the future. It is important to take into consideration that we need to set a certain portion of our tile cache texture to be used for the current frame and the rest for the tiles that are not visible anymore. That is what virtual textures basically are. A sparse approach of depicting only the parts of a texture that is visible or necessary, storing them in VRAM and streaming them to the GPU for fast depiction, while getting the rest from SSD by predicting which ones will be needed. Now, the question is, does this solve our problems? Looking at memory, we don't have to load the entire mipmaps to display only a fraction of them, like we can see on the left, but we can instead just use the parts that are needed and visible and hence use up less memory, like on the right. However, this can take a toll on performance. In this case, we are talking about streaming virtual textures, which focuses on optimizing memory usage by only loading visible texture data into VRAM as needed. It is a system designed to handle massive textures, like open world games, without overwhelming VRAM. However, it can overwhelm the computational portion of the pipeline and introduce lower performance and a lack of dynamically generated content. On the other side, we have runtime virtual textures, which are more about real-time texture rendering and sampling. It's essentially a render target that behaves like a texture designed for procedural workflows and dynamic updates. In this example, it can help us blend the two materials together, the stone and the sand, so we have a seamless transition. As opposed to the latter, it consumes more VRAM because the rendered texture needs to stay in memory, but the GPU efficient sampling is fast, improving performance. Whichever we choose, we have to know that there is a 1 to 3 millisecond budget requirement, meaning that there are additional calculations to be done on the GPU, which is the overhead, in order to predict and sample the adequate textures and their size, which means that if we need to optimize our frame rate due to GPU thread being over budget, this is not the way to do it. So if we have all our textures visible at all time, we should not do any streaming. Also, if we have textures that are less than 1K resolution or where Mipmaps are fully visible, we can just stream the adequate Mipmaps. Only when our textures are 2K and higher and are partially occluded in better part of our scene should we consider streaming virtual textures to make it worthwhile. So today we've embarked upon a journey of understanding how different physical memory units and virtual memory techniques are used within the memory hierarchy to transfer the information to the CPU and GPU and its role within the real-time rendering. And we also covered the most important terms and elements related to texture in the real-time rendering aspects, understanding how bitmaps are made and stored, how we can compress them by losing minimum detail, how we can optimize their resolution using various bitmap levels, and how we can stream only the visible parts of the textures to save up on memory and performance. Now, with this knowledge, little Kevin can grow up to understand how to make the same looking truck, but that is computationally less expensive and hence staying within the budget, like he did when he was left alone all those years ago. But textures aren't the only element in real-time rendering that faces challenges of scale and complexity. Just like textures, geometries must also be optimized for performance through techniques like level of detail. However, traditional LOD systems often lead to issues like popping, where sudden transitions between detail levels becomes noticeable, breaking immersion. What if we could take the ideas of virtual textures and apply them to geometry? Imagine a system that dynamically loads only the visible parts of highly detailed models, much like virtual textures handle tiles. This is exactly what virtualized geometry system is designed to do. How does virtual geometry system such as Nanite enable us to render billions of polygons in real time without overwhelming memory or performance? That's what we'll uncover next time. Now, here's the thing. Subscribing to this channel can be our little secret. No one has to know that you found these insights helpful. You can go to your settings and make all subscriptions private so neither I nor anyone else knows you support the channel. Whether you hit that button openly or covertly, it's up to you. But remember, every subscription, comment, or like is like casting a vote for this content to reach more curious minds out there, giving me feedback if this is viable or not. At the moment, not even 20% of people who watch videos are subscribed. So if you found value here, give the algorithm a nudge and maybe, just maybe, help someone else embark upon this journey. I thank you for your time and hope to see you in the next video. Bye.